Alright, in this example what we want to do is we want to write an energy equation for each of the cases here, and then we'll look at the energy equations. So for part A, we have the object moving. Well, actually, wait a minute, before I do that, let's say we have the object, so we know we're going to have kinetic energy. We don't change vertical position, so we're not going to have EG. We have a spring, so we're going to have elastic potential energy. And we're not told, let's see, actually we do have, looks like we have a rough surface. So we're going to have dissipated, whoops, not work dissipated, energy dissipated. Energy dissipated or work by friction. Okay, so now we're ready to do the diagram. So part A, we have the object moving, so we just have to pick. That's our first case. And it's moving, so kinetic. It hasn't slid across the surface yet with respect to the diagram series that we have. Location B, okay, it slid a little bit and just contacted the spring, but it hasn't started compressing it yet. So kinetic and just a little bit of dissipated. C now, it's completely compressed the spring. And it's traveled a little bit further, so elastic, and then the dissipated has grown a little bit. By the time we get to D, now the spring is back to equilibrium position, which means we don't have any more energy stored in the spring, but we have kinetic energy. But we've moved some more across the surface, so more dissipated. And then now E, we're told that the object is stopped and it's moved to distance D. Oops. And if it's stopped, it doesn't have any kinetic, the spring's not compressed, so all the energy must be stored as dissipated. That takes care of our diagram series. What that tells us then is between each of these diagrams, we can write an equation relationship. So for A, we have kinetic plus nothing, actually. We just have kinetic. For B, we have kinetic plus dissipated. For C, we have elastic plus dissipated. For D, we have kinetic plus dissipated. And for E, we have dissipated. Let's suppose we wanted to know, I don't know, it kind of depends on what you want to know, what you set equal to each other. But we could say we want to know how far is the spring going to be compressed. So let's suppose that's the question. If that's the question, we're interested in diagram A, and then where the spring is compressed at diagram C. So we would say kinetic energy initial is equal to elastic potential energy plus dissipated. Well, kinetic energy we know is 1/2 mv squared. Elastic energy we know is 1/2 kx squared. dissipated is force of friction times how far we've traveled. Now, since I called this one X, I'm going to call this one something else. I'll call it D. And so our D would be how far we've traveled. So surface travel distance from A. X is just going to be spring compression. And then you'd have to know force of friction, spring constant, initial velocity, and mass. And then you'd be able to solve for whichever one of those you didn't know. Another question could be how, or what is D? What is capital D? Calculate that. In that case, we'd need to know A and D. So we'd have kinetic energy is equal to energy dissipated. And so we'd have 1/2 mv squared is equal to force of friction times distance. So then D is still going to be the surface distance traveled. And of course force of friction, and so we would be able to calculate what D is based on the size of force of friction and then how fast we were traveling. Now what we'd have to be careful with this little d, notice the little d is not quite capital D, because the object is going to travel from here, compress the spring, and then come back to this location called D. So this distance right here, F we'll call it just because I have to pick a letter, plus this distance right here, G let's call it. What I've called D is actually F plus G, the total path length. It's supposed to be an L, there we go. And D is just a component of that. If you look at your original diagram up here, D is just the distance from the end of the spring to where it stops. And so maybe get a little note here, includes spring compression. Let's see, would there be another question? Okay, another question that you could ask for a series like this is, how fast is the rebound velocity? If that is the case, then we're interested in A, right, because it will allow us to calculate the total energy in the system, and D. Well, A is kinetic energy. D is kinetic energy plus dissipated. And so we have 1/2 mv, 0, we'll call it 0 squared, equals 1/2 mv squared plus force of friction times D. And again, D is path length. Now this path length is also going to include the compression. All right, takes care of that example.